It's fine.
Okay, so hello everyone. I'm really happy to organize this next seminar in the series of the seminars that our laboratory is holding this July and August. And today we are very pleased to listen to Vasilisa Vashchenko, our young researcher of our laboratory, who will be talking about hierarchical stochastic block modeling for topic modeling, and this topic is based on Vasilisa's bachelor's thesis. Vasilisa, we are really happy to have you here. Even though Vasilisa doesn't feel so good today, unfortunately. So Vasilisa, please be sure that you are fine. And if you will not be feeling good, so just let us know. Yeah, we are really, we are really happy that you managed to come. Yeah.
Thank you for understanding and for the kind words. I do indeed feel a bit weird. So if you just excuse me, I will be talking less loud than I usually would. So if I'm speaking too quiet, please tell me. I will try to raise my voice. But like the quieter I speak, the longer I will be able to do that. And if you excuse me also, I will not be turning my camera on, if that's okay. So I think the preface is enough for now, and I will carry on with my presentation now. The topic is actually a little bit obsolete because I did not change that from the summer school, but this time I also included in the presentation some information about the other methods for topic modeling that I employed in my thesis and that I would like to talk to you about. So today I will cover some basic theoretical background, basic theoretical points, methodological points for 3 different methods for topic modeling, and I will provide you with the resources to study them on your own, as well as I will attempt to demonstrate how they work and how they can be implemented on 2 different cases, depending on whether my ability and the time is sufficient to do all that. But we will be talking about 3 different methods. To begin with, I will swiftly cover some of the descriptive information about my study, about the thesis that I wrote, that I prepared, and based on data from which I will be talking about comparing those methods on pretty large data sets. Well, I'd say those are medium-sized, but in comparison with what I will be able to show you real-time today, those are larger. So my study was on discovering the latent topic structure and or comments on the urban theme TikTok videos. So I collected data by scraping TikTok, and I managed to get my hands on a little bit more than 150,000 comments from 1,200 videos. And surely you can, again, reproduce that on a larger data set, and I will be probably doing that also, but the results that I will be talking about today are based on this data set. So just so that we are on the same page, I want to describe the data set and just a few details, because what we have to keep in mind here is that the data from social media is vastly different from the information and the textual data that you would find elsewhere, and that many methods for textual analysis are developed on, because if you read the majority of articles that are talking about developing a new method for textual analysis, you will probably find a description of a data set that consists of long texts and very well structured text. So, for example, even one of the methods that I will be talking about today was developed based on Wikipedia. And Wikipedia is a corpora of very large texts. The majority of articles in Wikipedia are pretty long. And also it is a corpora of texts that are well structured and are grammatically correct, because those articles are proofread, those articles are peer reviewed, if you allow me to say that. And thus they are easier to analyze, whilst data from social media is comparatively chaotic, because here we do not have that much of a structure. We have a lot of typos, a lot of spelling mistakes, and that on the one hand is pressure on the pre-processing step for the analysis. So when you analyze the data from social media, any data from social media actually, you have to spend a lot of time resources on pre-processing your data and cleaning that, but also you have to make sure to use the correct method that is applicable to that type of data, because some of those are actually not well aligned with the, again, the chaos and the abstractions that are posed by the structure of social media data. So that is probably the introduction about the information that we have in our hands. That's sufficient. So let's move on. I will also just very quickly cover the key ideas about what we are doing here. The key topic I will be raising today is topic modeling, and all the algorithms are concerned with topic modeling. Topic modeling is a set of techniques that are being developed and applied for unsupervised text processing. And for those of you who might not be well acquainted with the terminology, unsupervised analysis, unsupervised modeling just basically means that we do not know the correct answer. So when we are trying to model something, we are just optimizing the end result without being able to compare it to some factual representation of the correct information. So on the one hand, when we are working, for example, with something like regression, we have the correct answer, and we are trying to optimize the parameters for our model to suit that, whilst with unsupervised processing and modeling, we do not have that. And topic modeling, again, searches for latent representations and latent patterns in data, and does not try to approximate some correct, quote unquote, representation, but rather searches for hidden distributions of data. And topic modeling, each algorithm for topic modeling as the end result produces semantic clusters of words and expressions. I am putting words and expressions separately here because we can agglomerate words, cluster words together even before we form semantic clusters. We can produce, for example, bigrams, trigrams, so we can just agglomerate different expressions into a single token. And those will also pose as a single token moving on forward. And the third point that I want to make here is that topic modeling is different from topic classification, because here we are not attempting to classify documents to like link the document that we have before our eyes with some already predetermined idea, predetermined class, but we try to infer those clusters, infer those topics from our data. The next theoretical frontier that we have to cover and we have to cross is the discussion of latent hierarchical allocation. Again, I will be swift here so that we can quickly move on to the practical part, but the basic idea here is, and why we are actually discussing LDA, is that it is one of the most commonly used tools, probably not for long, because a few very important and not very drastic, but quite critical introductions or improvements in the array of topic modeling have been made during the past year. So I would expect that latent direct allocation is cornered a bit by those new algorithms. But for now, it remains a very commonly used tool. And as already mentioned, it attempts identification of latent semantic clusters, so hidden semantic clusters, something that is not evident and is not directly represented in the data, but that requires additional modeling. It is based on a more broad algorithm, but its distinctive feature is that it assumes a very specific distribution of topics in the dataset and distribution of words in topics. So just basically PLSI, a more broad version of what LDA is a tool that works by assuming or modeling some distribution of topics in the data set, and again, of words inside those topics, so that to approximate a preset distribution, and just like that, we form our clusters. So basically, depending on which distribution we decide on, we may end up with very different clusters and very different topics. In the case of LDA, we model topics based on, is everything all right? I heard some noise. Oh, I hope it is. Then I will be continuing. So in this case, we are working with a preset Dirichlet distribution, and that just basically means that those are the assumptions about how topics are distributed and how words are distributed in the topics. And the next important idea here is that LDA works with documents, with each document as a bag of words. That means here that for LDA, it is not important where the word is positioned inside a sentence. If we have a document, it just basically is a mass of different tokens for LDA. If we have a set word in the beginning of a sentence or the end of a sentence or a document, it does not make any difference. It just is important to LDA that the words coincide inside some window, for example, or inside the document overall. That just depends on the architecture and the like restrictions that we pose to our model. But basically, inside a set window, for example, like plus minus 5 words from a set position, it is not important where the word is positioned, which may be critical in some cases, and we will talk about that later. Here are a few illustrations that just represent the philosophy, maybe the theoretical insight behind LDA. So we represent each document as a set of words. So for example, in this first document has words dog, animal, loyal. The second one has words animal, cat, evil, etc., etc. And if we want to infer any pattern about how those words coincide together, how they co-occur, and any patterns of their semantical difference or on the other hand, similarity, we would have to look through all of those links between words and documents and try to infer patterns here. But introduction of topics creates this latent or hidden layer between the layer of documents and between the level of words. So it's some form of hierarchy. And by agglomerating words into clusters, we now have a new way of talking about the contents of a document. We can speak more generally. We can maybe infer more similarities, more important semantically similarities about how those documents differ or instead are similar to one another. And here, for example, from this picture, we probably couldn't infer much, or at least we would have to look at it for quite a while to make any corollaries. But here we can very quickly identify which topics are related to which document, and thus think of those documents as somehow related. Now, let's move on to the issues, to the downsides of this algorithm. So despite its very widespread and despite the fact that it is pretty much applicable to many corpora of textual data that we have for training our models, it has a few very important methodological issues. I will be focusing on some highlighted by the authors of the second algorithm I will be covering today. The first issue here is that LDA does not have a defined algorithm for deciding on the number of topics. So, for example, even in this case, just like an illustration, we don't have any formal way of identifying beforehand that we only need 4 topics, because maybe we would like to differentiate between, for example, AI, Dota, and cars. Maybe we don't want to say that AI, Dota, and cars are the same thing and are related to the same overall idea of technology. Maybe we want cars to be different or something else. Or maybe we want to differentiate between offline and online sports. So we have no idea of knowing which decision would be optimal here beforehand. So usually LDA algorithms operate with a preset number of topics. So the default number of several dozens, usually 100 topics are created, and then you can optimize them by hand manually to create the most interpretable and the most coherent topics out of the data and the algorithm that you have in your hands. That definitely does sound not exactly efficient. And for this reason, we would surely like to see a solution for the issue of topic modeling that could provide us with a definite answer as to why this specific number of topics was decided on. Then LDA is prone to overfitting, so it is more difficult to generalize and make inferences with on new data, for example, and somehow incorporate new documents into your baseline data set because of the large number of free parameters in the algorithm here that do cause overfitting. And also the other thing that is highlighted by the critics of the algorithm is that there is not exactly sufficient justification for the decision for the choice to implement Dirichlet priors here as the basic baseline distribution for topics in the data set and words in each topic, because almost every preset distribution and Dirichlet distribution in particular may contradict some properties of text that we know of and that linguists have discovered. So, for example, Gerlich and Bishara speak of the Zipf's law. They highlight that the Dirichlet allocation does not take into account that different words have different patterns of occurrence in texts overall. So we know for a fact that in many languages there is a small number of words that occur very often that are used every day by like thousands of speakers and writers, and those words occur very often. But there is also a very large array of words that are used rarely. And thus we may not, based on just this pattern of occurrence of frequency, we may not end up with a solution that is efficient for those words that are rarely used, or in some other cases, we may just exclude too much semantic information from the words that are occurring often because we think they are not as semantically important because they occur so often. So there are different issues, linguistical and technological here, that we have to be conscious of, and the choice of any preset distribution for the number and the pattern of occurrence of topics in our data set does not allow us to solve this issue properly. So what do Gerlach and Pichota suggest us? I will return to this slide a bit later on, just to demonstrate and compare the results. But for now, I'll go further with my presentation. I will now be speaking about the article of those people who provided the critique I just covered of Gerlach, Pichota, and Altman. They are scholars in the array of network science that suggests usage of hierarchical stochastic block modeling for topic modeling. The idea is pretty similar here. They suggest that we can conceive of the word document matrix that is used in topic models as a bipartite network. Just philosophically, let's look at it for now. In the picture on the right of the slide, you can see the ideas. On the one hand, we can represent our documents and words that are present in those documents as a matrix. So we see, for example, that such words as the or of are omnipresent in each of the documents, and words like football or science are rarely present together. So only document B has both of those words, and generally they occur separately from one another. So when we aggregate the data that we have here into some heat map for frequency of occurrence for each of the words, we can see the outline of occurrence patterns for each of those words. So we see that, for example, documents A and B have the word football in them, and documents C and D have the word science in them. And thus we can suggest that maybe documents A and B are similar in that they talk about sports and football, for example, and documents C and D are also similar because they talk about science. The same result is achieved by representing this matrix as a bipartite network, where we have two different types of vertices, on the one hand the words, and on the other hand the documents. We may arrange the groups in the same manner. Again, we see the semantically unimportant the and of, but we see surely also that there are those small communities on the one hand of the documents that are connected with football, and on the other hand the documents that are connected with science. So this idea is developed further by suggesting that we may conceive of the generic stochastic block model as a more general version of the baseline that underlines LDA. So in the very foundation, like mathematical and statistical foundation of the models, they are pretty much equivalent. And thus, having suggested and having proven that, and I'm giving you a link here because the authors go into pretty much detail on how this equivalence is proven and how it is important for the overall discussion. So I do generally suggest that you click on the link and go there. I will show you the presentation as a file. I will link it in the chat a bit later, but the article is very good to read. So they have proven that statistical equivalence between the stochastic block model and PLSI. And then they suggest that for development of a topic model, of the most optimal topic model for different texts, they should go in a different direction that LDA is going. Because instead of choosing a singular distribution, a singular prior, or in this case, Dirka prior, they suggest choosing a hierarchy of prior. So they want their model to be agnostic about the underlying distribution of the data that is provided to it. And thus, choosing a hierarchy instead of a singular prior allows to catch very different patterns in the data. So more sparse, or on the other hand, small and small and interconnected topics, and topics that are differently distributed in the data. By introducing that hierarchy, we see different topics, and also we can take into account the topics may come in different sizes, in different shapes, etc., etc. So this hierarchical approach in clustering the documents and clustering the tokens is what theoretically would allow the approach developed by the authors here to be more applicable to different types of data. So because it is more agnostic, because it does make less assumptions about how what the data should look like and how it should be distributed, they can make inference on very different data sets. Let's move on here. So I will show you the topics that resulted from using different algorithms in my thesis, so on my data. Again, as I've mentioned before, I was working with a data set of Russian urban-themed videos and comments that were left onto those videos. So the topics and the word examples here are in Russian, and I am very happy to translate in case anybody needs that. But for now, I will just generally cover the patterns of distribution of words that I can see here. Well, first of all, I want to highlight that unlike other two algorithms, and we will speak on that again further, unlike the other two algorithms, HSBM create very different topics. And for example, it did catch up with the fact that in the data set, there are different languages. Despite me filtering the data based on Russian hashtags and looking for the videos so that all of those are in Russian, some of the comments may be left by non-Russian speaking users, or maybe left by Russian users, but not in Russian language. So there is, for example, English language and Ukrainian language also. And what we see here is that the fact that there are very little of those comments, just a few of them, produces the topic that is very semantically incoherent, but formally coherent, because all of those words are English words, or all of those words are Ukrainian words. If we had more comments of any of those languages, we would have probably semantically coherent, semantically interesting and interpretable topic. But for now, we just see that the idea that unifies the words in the topics 10 and 11 is the language that they are written in. And HSBM does define that, but not the LDA nor BERT topic did see that. And again, we can discuss whether or not that would be necessary or whether or not those words should be filtered out. But that is just an overview of the level 1 hierarchy of topics that HSBM produced in my case. Other than that, we see also very different topics because on the one hand, we have topics that are clearly related to some ideas. So for example, there is a very politicized topic speaking about Russia, Europe, Ukraine, America, jealousy, Putin, etc. On the other hand, we have more urban themed and specifically themed to align with different aspects of urban life. So for example, public transport, again, public transportation, something having to do with working, living in the city. Other than that, there is a very formal topic that just unites words that are introductory, that are congratulations, etc. So those are actually like acts of speech instead of being full-on expressions. They do not convey any further idea rather than their immediate contents. And this is the level 1, but again, thinking about the philosophy, the baseline methodology for HSBM, we have a hierarchy here. So those topics can be aggregated into larger groups. And on the level 2 of the hierarchy, we only have 2 topics. So if we take one step further, then the algorithm says that the most optimal way of speaking about this data set would be to define it as consisting, comprising of just, being comprised of just 2 parts. On the one hand, it is urban life, it is words that have to do with the city, with living in the city, and on the other hand, there is politics. So pretty much that same politicized topic. And again, having played a little bit more with different levels of the hierarchy and larger data sets, you would be able to see the patterns and how they are agglomerated and how the clusters are combined to create something larger when you request that the other level is shown. And again, I think that this is pretty much important because we see that the decision to define those 11 topics versus those 2 topics, those are very different like baseline functions of combining words into groups because here the logic is more diverse and more topics are thus created, but when we want to agglomerate them, we are looking for a larger pattern in the data, and thus we end up with just 2 of them. Speaking of the LDA algorithm, I was working with an adaptation of that that also includes introduction of word embeddings into the algorithm as it is. I will link the GitHub page of the R package that allows you to do that. I did pretty much the same thing but in Python. And you can look into it, I think, yourself. I would probably not recommend that you work with it in R, but you can surely do that. I prefer to do it in Python because I believe the preprocessing libraries to be more optimized for and more diverse for Python than for R. But this specific package is available in R. You can choose different embeddings to work with here. The package that I linked in the chat just now, it allows you to train your own word-to-vec model before you begin creating topics. But I was working with an array of embeddings that were pre-trained. Those are static embeddings, which just means that there is a specific numeric representation for each of the words that we have in our vocabulary, and that representation does not change independent of the context. So, for example, even if we have a word that is homonymous with another word that has a different meaning, they would still have a joint numeric representation, which is suboptimal in many cases, but it actually, this approach does actually work quite well in a lot of cases where you do not need to create, for example, complex sentences, but rather just analyze some of the semantic traits of the data. So, for example, for classification, that would be sufficient. And in many cases, for automatic modeling, that might also be sufficient. We'll look into that, but there is another idea here, the idea of LDA, the product LDA. And I believe that that is primarily what makes the decision a bit suboptimal. And I think that you might end up with a bit different result if you use the R library, but I will just in a minute show you some of the topics that were created by the algorithm here. That is, again, the same algorithm as what they have in R there, and the negative trait of this particular implementation is that it does not take into account the idea of exclusionary word allocation. So if a word is already in one topic, there is nothing stopping it from occurring again and again in all of the different topics. So in my case here, this implementation did end up with very similar topics because of this greedy approach, and those topics are pretty poorly differentiated from one another. Excuse me, I'm just lost track of the file where the topics were collected. So I think I'll make a small pause here and return to the presentation, but I will show that to you going on forward. For now, I think it's not exactly important. I'll just state for a fact that the end result of this algorithm was some dozens of pretty poorly interpretable topics because of the non-exclusionary approach, because the same words did occur in multiple topics. And those words were primarily actually the ones we have seen here. So those that ended up in topics 1 and 2, those are the most numerous topics, and the words that are included in those topics are very high frequency words, even though some of the most high frequency words have been filtered out from the data set. But let's just take a look. I actually found the file. So those topics are not identical, and you have to take into account that what is shown here is only the top 5 words for each of the topics, so they are more differentiated further down the line, but you can see that a lot of words that are high frequency just occur in all of the topics, and that is the negative trait of this particular implementation, but again, it can be used differently, and haven't introduced the option for exclusion, we would probably end up with something a bit more interpretable and high quality. But that's what we're working with for now. I'll just also say a few words about what was done here. The idea just was that we can enhance the performance of LDA by supplementing it with pre-trained embeddings. So not just expecting the algorithm to infer all of the important patterns on its own, but rather work with some already existing baseline that can be drawn upon. And for this baseline, I chose Naviek, a part of Natasha library for the Russian language. Those are actually very great for many of study projects and maybe some commercial projects for the Russian language, because they are very small, they weigh almost nothing, and the vocabulary size nonetheless is pretty comparatively big. It is sufficient for the majority of uses, especially academic uses. So again, in case you want to reproduce something on your data set with Russian words, I would choose that, but there are a lot of different embeddings that can be used for the task. And here I just send you to Rus Victoria's website, where you can choose for yourself. And I, for now, will be moving even forward to talk about the third algorithm that I used here. The third development in the array of topic modeling was per topic. That is, well, as a library, as an implementation, it is comparatively novice, and as a form of more like independent developments surely existed for a longer time, because the basic idea is comparatively easy. The novice part is actually the stacking of all of those ideas together and introducing them as a form of a tool, of a working mechanism, like a library for the Python programming language. But the basic idea is, again, basic in this case. We have at the foundation of the algorithm, like the lowest Lego detail, a pre-trained transformer for, well, in this case, I believe that it was a multilingual model. And from this sentence transformer, we retrieve embeddings. So the way that the model represents the documents, we want to receive that numeric representation. At the second step, we work with those embeddings to reduce the dimensionality. Basically, this model combines the idea of clustering documents and clustering words. And if you apply it to your own data set, you will receive as an information memo, you will receive the summary of how each topic is represented in different documents. So I will show you later on how for each topic we can receive a few of representative documents. So we retrieve embeddings, documents embeddings from the underlying transformer model. Then we go through the step of dimensionality reduction before we go further to the clustering step. An important idea here that is, again, expanded on in the website and in the article that the authors of this approach created. I will also link the website that you can visit to learn more about the algorithm in the chat right now. So the important idea here is that this solution is in fact very similar to Lego as a game. So that is why it is represented and illustrated here as such. So you can take different steps of this pipeline, of this analytical pipeline, and exchange them with other equivalent solutions for this exact step. So for example, if you do not want to work with UMAP as a dimensionality reduction algorithm, you can replace it with PSA, for example, or TSNE if you want to. So any other dimensionality reduction solution would work as well as you can replace the suggestion for clustering method that is included as a default by the authors with something different. But basically, that is how the default solution looks like when we represent it as architecturally. So after the dimensional reduction, they go on to clustering. And I want to bring your attention to the fact that clustering here is also hierarchical. And that allows this solution per topic to reach the same positive and high level of quality and also solve the same issue that the authors of the previous approach had with LDA by being able to catch clusters of different size, different density, and different shapes. Basically, then the words in each cluster are tokenized, and those tokens are weighted to to refine the clusters. Let's explain this like this. The probably something not very familiar here is the CTF-ADF step, which is actually the same thing as the classical TF-ADF, which is an algorithm for weighting, like assigning weights to words in the documents. And via TF-ADF, you can filter out unimportant, quote unquote, words and make it so that only the important, the critical and semantically loaded words remain in your corpus. The CTF-ADF is an adaptation of that for cluster-based approaches, because the C here stands for class. So before the TF-ADF procedure is performed, the documents in each of the clusters that were created during previous steps are aggregated into one singular very long document. And then inside that document, the words are assigned their weights based on their total frequency and their inverse document frequency. So we want only the important words, only the words that are specific to this particular cluster, only the words that do not occur all that much, but also occur enough to be semantically loaded and to be noteworthy, to remain at the top of the list of words for each cluster. So after the words are weighted, we think of the clusters as refined, and the words that end up at the top importance levels in each of the cluster as most representative of that particular cluster. Well, then, as the final step, it is optional. You can play a bit more with the representations. Here, I will not go into detail. You can take a look, look into it on the website of the algorithm. The authors do cover all the already implemented opportunities for transforming representations, but it is irrelevant to our discussion here. I will show you the topics that are resulting from implementing this procedure, this algorithm, to the data set that I was talking about previously, the data set from Urban TikTok comments. We can see topics of different size, and again, I will show you in a minute the hierarchy and the distribution of documents for each topic. They are pretty diverse. I want to highlight that first, there is an issue with disproportional clusters, disproportional topics. So you may end up with a cluster that will be comprised of the majority of the documents that you have in the data set. This can happen, whilst some other topics will be relatively small. This actually happened here because topic 0 did have dozens of thousands of documents attached to it, whilst some of the other topics only had a few hundred documents that were related to it. But in some cases, this might be indicative of a problem. In other cases, might not. But that is something to, again, be conscious about, be conscious of. Another maybe negative issue here that I have noticed is that in some cases, because of the I think the specifics of the representations of the words here, we can receive documents that receive topics that are not exactly related, not exactly coherent in terms of the words that are inside, but would be coherent if we were just talking about the tokens that are a bit smaller than the words. Because let's look at topic number 8. So the words here are not exactly, like, not all of those words are related semantically. Top 3 are like cat, female cat, and a more how would I say that? Like a gentle representation of the word cat. So like a kitty cat. And then we have at number 4 and number 5 words that are absolutely unrelated to the topic of cats, but are written a bit similarly. And here we again run into the problems with the way we represent words when we speak of those algorithms, because as I mentioned before, for static embeddings, you would have the same array of numerals representing homonyms, so the words that are very similar to one another, the words that are, basically sound the same. In case you do not have a part of speech tag, you may end up with those words lumped together in your vector representations of the words. But in this case, I believe that this topic was comprised of words that consists of very similar tokens, like parts of the word, because kotelnik here, I believe, stems from the name of the metro station, Kotelniki, and kochka, also like a bump, does not have anything to do with cats. But other than that, we can see that many of the topics are indeed pretty coherent and pretty specific, in fact. So we see defined some urban themed topics that have to do, again, for example, with public transportation. So bikes, bike lanes, bicyclists, like cyclists, etc., etc. We also have some very small and specific topics having to do with territorially local issues, and that were making sense at the time of writing the comment, because they are very related to a specific video, for example, so the topic that was raised in that video, but might not make all that much sense outside of that context. So we overall just can see that based on some downsides of the algorithms that we covered, as well as the specificity of the Russian language, maybe a bit poor quality for some of the models that are pre-trained for the Russian language, we see some poor quality topics and some higher quality topics. And basically, for each of the algorithms that we are working with today, you would have to make some manual adaptations for the number of topics, and sometimes you would have to lump them there together, or want to, on the other hand, differentiate between them. The good part here, though, is that you can do that, and why I am so excited about the word topic library is because it does allow for a lot of experiments and adaptations that you can do for yourself. And this last slide of the presentation demonstrates some of the criteria based on which I compared the models that I employed for the data set. Here you can see that based on that criteria, or number of topics is not exactly like a metric, it's just something that I wanted to be implemented here so that we can compare how differently each of the models produced those topics. But what we can compare and what we should compare is the computation time. So the amount of time that it took for each model to converge and produce results, and coherence scores. I infer the majority of quality from UMass and PMI because CV is less indicative of quality coherence, but actually based on each of those metrics, we can see that BERT topics, so the last approach, outperforms its alternatives greatly. It is faster and it produces more coherent topics, but depending on which metric we want to look at, we will see different gaps in the quality. Because, for example, based on UMass, we would think that ETM is a lot better than HSBM. But when we take a look at the CV metric or the NPMI metric, we do not see all that much of a difference. So that just stems from the way each of those metrics are calculated. And again, if you wish to, I can provide you with more information and resources about how all those metrics are computed, so that you can make those comparisons again for yourself. But each of them are implemented, just numerically are implemented in the GenSim library. So there is that, and with this we can probably finish the presentation with the slides, and I will just swiftly show you some of the possibilities of the BERT topic library and the other algorithms that we worked with and that we talked about in the code. So I think that probably just another like 10 minutes of your time. Give me a second. I will change the demonstration and show you the code.
Dear Vasilisa, thank you so much.
That's it. I guess, I just wanted to show something about the BERT topic library and the functions that it has. I will be swift, and then I will end the presentation. So here I was working with a data set, like actually a pretty random data set from the Hugging Face datasets library that consists of news excerpts from Nigeria. And it has different groups of documents that have to do with sports, politics, business, etc. First of all, the model is computed very quickly. It only took a few minutes for it to make the inference. But in this case, the data set is really small. It only has like 5,000 or 7,000 documents. And I just want to show you some of the important functions. First, to make the inference, you would run fit transform with the model to retrieve the topics and the probabilities for each document to be assigned to that topic. Okay. I will show you what I already have computed. You can also manually reduce the number of outliers because, as you can see, this model here also creates a separate topic for the words that it couldn't and the documents that it couldn't assign to any other topic. And it so happens sometimes that the number of those outliers is actually pretty critical, so you would want to reduce that, and you again can manipulate the strategy and the approach by which you reduce outliers according to your taste. You would then receive the overview of the topics that are created by the algorithm. And what I really like here is that you can visualize very quickly the hierarchy of all of those topics. In some cases, for example, in the case of my data set, the first automatic solution created several hundred topics. And sometimes if you have a larger data set, you would end up with several thousand topics that you cannot go through manually. And here, the hierarchy would not be very readable, like legible. You wouldn't make an inference based on that. But in this case, because we only have a few of the topics, we can look at it, and you can see the importance and like the pros of using a hierarchical approach, because we can specifically see where the documents align and where they diverge from one another. So, for example, here we see a few of the topics at the top of the illustration. So, something having to do with vaccines, COVID, vaccine, etc., Pfizer, COVID. So those are basically the same idea, but with probably some different aspects to it if we look at the representative documents. And another example, like we see that, for example, here, Facebook and WhatsApp are different to different topics. And here we see something talking about Twitter and Facebook, but at the other level of the hierarchy, they are represented at the same topic. So why this is important is because this would allow you to manually manipulate and recreate the topics that you would want to have. Basically, you can assign the number of topics that you consider optimal to the algorithm. You can say that you want to only see, for example, 30 topics or 10 topics, and the model will recreate those topics according to your needs. And this hierarchy is a good representation of that. I probably now will end my presentation. I think I'm run out of time. If you have any questions, please do not hesitate to address me. And I will also link the codes, the notebook with the codes in the chat. So if you're interested in that, you can go through it yourself and recreate some of the results. Thank you for your attention.
Vasilisa, thank you so much for your very interesting and insightful presentation. Dear colleagues, do you have any questions or comments or some ideas? Okay, probably while you are thinking, I can ask a question to Vasilisa. Actually, my question was answered by Vasilisa in the last several minutes when you showed this great picture showing how different topics are connected. So actually, my question was like, is it possible? Is it possible to visualize the hierarchy of different topics, how they are connected, so that you can cut at several levels for all these algorithms? So now you was showing us BERT topic algorithm, and definitely we see that yes, it is possible. And what if we are talking about this stochastic block modeling algorithm, and also another model that you was using in your work?
Yeah, sure. I will was just looking for the graph. It's dispersed from the notebook for now. Like I said, code, but I would have to run it again. So just give me a second. I will show the graph that resulted from my data sets that I used in my thesis. So you wouldn't be able to do that with the ECM algorithm because it is not hierarchical. You can, if you want to compute similarities and like semantic connection between each of those topics, because it has to do with embedding, so you can work with them as vectors. But for per topic and HSBM, because those are hierarchical, you can see the relationship between topics. But sometimes those are not very insightful. So for example, again, if you have like hundreds of topics, you probably wouldn't be able to look through them properly. But here, for example, let's take a look at the graph that we have here. Let's just explain, it's not exactly symmetrical because the visualization algorithm assumes that in my case, it is pretty symmetrical, but it assumes that the documents have titles. So on the one hand, you would have the titles of the documents. On the other hand, you would have the documents as well. And they are processed and clustered separately from one another. So you would oftentimes see with your data that the left and the right side of this graph would look differently because the titles and the words are the titles and the documents are processed differently. And it was actually more insightful with the data set that I wanted to show in the notebook because the news articles actually had like specific class groups, and because they were collected like that, so it was just more legible. But basically, you can see that each step, each point here is a cluster, and at the like third level of the hierarchy, the clusters converge into just one big cluster. But as you step further away from it, you have more and more groups that are further collected if you want them to be aggregated.
Great, thank you so much. And do I understand correctly that you would advise us, for example, if we would like to analyze some set of news, if we would like to identify the topics, so it is more preferable to use their topic model, or
I
they
would
are
say
different?
that,
Yeah.
I'm sorry for interrupting your question. Well, I think that it is preferable to use per topic in case you're running out of time, because it is a lot faster, and depending on the size of your data set, it may be critical to cut the time spending that you have to endure in order to receive the inference. But also you have to be mindful about the downsides of per topic as well. As I showed previously, it may also produce poorly interpretable and not exactly semantically aligned, but formally just aligned topics. So I probably would choose per topic if I had to work with a large algorithm, because even with a large data set, because even with my data that was pretty small by industry standards and academic standards, I had to wait almost 4 hours for HSBM to converge. But if you have something even smaller, so like 10 to 20,000 documents, it will be pretty swift, like comparatively and appropriately quick, so that you can also choose that. And I think that maybe in some cases it would work even better. But that also depends on whether or not the hierarchy of topics is of first or second importance to you, because the SBMTM, so HSBM library, allows you to visualize the hierarchy of topics in a more insightful way, and the authors also have a tutorial on multi-level agglomeration. So you could work with networks of different types and create a hierarchy for a bipartite network, or even a network of more modes. So for example, a tripartite network, if you want to. And those features are not available in Bird Topic. So if you prioritize network analysis, then HSBM is probably the tool to go to.
Great. Okay. Thank you so much. Dear colleagues, do you have other questions?
Oh, if not, then I
Okay.
wave my goodbye and thank you for your attention.
Yeah, thank you so much, Vasilisa. Yeah, I think it was really interesting. And so today we were talking about the comparison of different algorithms in the usage of topic modeling. And next Wednesday, on August 2, we are going to talk about comparison of different approaches to block modeling. And this topic is somehow connected to the topic of Vasilisa. At least there is the same word of block modeling. So dear colleagues, please come and join us this Wednesday. The seminar will be held at 4:30. So please be sure you will be in time. So Vasilisa, thank you once again. Dear colleagues, thank you for coming, and see you on Wednesday.
Thank you.